Hello gang. Today we're going to talk about creating energy bar charts and using energy bar charts to show transformations in energy within a system. Energy bar charts are also known as LOL charts because they're so dang funny. Actually, the reason why we call it an LOL chart is because the shape it takes actually looks like the letters LOL. So it's used to show energy transformations within a system. So the first thing we need to understand is that each bar chart is representing a different point in time. The left-hand side of the chart represents the initial energy of the system, whereas the right-hand side of the chart represents the final energy of the system. Now keep in mind, this could just be the energy at two different points. It doesn't necessarily have to be the complete beginning and the complete end of the time frame that we are looking at. Within the chart, we have three different types of energy. The TME stands for the total mechanical energy, PE stands for potential energy, and KE stands for kinetic energy. Keep in mind that the total mechanical energy is the sum of the potential and kinetic energy. The circle in the middle is used to represent the system that we are working with. When we identify the system, we are going to write what object is in the system. It is also used to show the amount of work that is being done on the system between the initial phase and the final phase. When we're using our bar chart, we have to remember the law of conservation of energy. Keep in mind that energy cannot be created or destroyed. So whatever the total mechanical energy is at the start of the system, it must be equal to the total mechanical energy at the end of the system. That is, unless work is being done to add energy to the system or remove energy from the system. So let's look at an example. An egg is dropped from a window as shown to the right. The letters within this chart are showing the egg at different positions during the egg's fall. Let's assume that this egg starts at rest. The first thing we want to do is identify what we're calling the initial phase of this drop, which I am going to call position A. Then I want to analyze what's going on with the egg at position B. So once again, we don't necessarily have to call the second chart the complete final position. I want to look at what's happening at position B during this fall. Next thing I should do is recognize what my system actually is. Well, the object that is falling is the egg, so let's write the word egg in the middle so we know that the egg is the system or the object that we are really concerned with. So now let's take a look at what types of energy are present during this fall at position A. Well, at position A, we said that the object was at rest, and it is elevated. So let's think about what that means. If the egg is elevated, that means the egg is going to have potential energy. So what I'm going to do is I'm just going to draw a bar that is representing the amount of potential energy that the egg has. Now, we're not going to be dealing with numbers to start with, so I could just make this whatever size I want. I made my potential energy a total of 6 units high. Now, because the egg is initially at rest, that means the egg isn't going to have any kinetic energy. So I'm not going to put in a bar for kinetic energy because it's not moving at position A. What this means is that all of the energy that the egg has at the start is in the form of potential energy. So the total mechanical energy is equal to the potential energy that the egg has. Well, what about position B? Well, because of the law of conservation of energy, we know that the total mechanical energy has to be the same. There were no external forces acting on the egg other than gravity, which we will not consider as doing work on the system. Therefore, the total mechanical energy is still going to be 6 units, which I'm going to show at position B. Well, did the egg keep the same amount of potential energy the whole time? Well, it couldn't have because it lost elevation. As a matter of fact, it went to about half of the height that it started at. So I'm going to say that the egg now has about half the amount of potential energy that it started with. So if energy can't be created or destroyed, where did those other 3 units of potential energy go? Well, keep in mind the egg is now moving. So that means that the egg is gaining kinetic energy. So whatever potential energy that the egg lost, it was transformed into kinetic energy. So this is what our bar chart should look like from position A to position B. The total mechanical energy stayed the same. The egg lost 3 units of potential energy and gained 3 units of kinetic energy. Let's look at this drop for position C. Now first I want to look at what it's going to look like right before it hits the ground. So let's say it gets as close to the ground as it can without actually striking the ground. Well, we're going to look at the comparison between position A and position C. So my energy chart for position A should remain the same. Well, what's happening at position C? Once again, there isn't anything that's adding any force to the egg that is going to change the egg's total mechanical energy, because we're looking at the point right before it contacts the egg, the ground, that is. So therefore, the total mechanical energy is still going to remain the same. Notice now at position C, the egg is as far down and not elevated as it possibly can be, which means that the egg must have lost all of its potential energy. So where did that potential energy go? Well, all of its potential energy is going to be transformed into kinetic energy. Let's think about what this means. If we see that energy bar chart on the right, what this means is that it has no height, which means it has no potential energy, and the kinetic energy is as high as it's going to be for this egg's descent. This also means that the egg is going to be moving its absolute fastest at this point. All of the total mechanical energy has become kinetic energy. Now let's look at what happens when the egg actually strikes the ground and comes to a stop and splatters all over the ground. Once again, I'm going to compare position A to position C just after it hits the ground. So at position A, I'm going to have the same amount of total mechanical energy and the same amount of potential energy. Well, this time, if it hits the ground and it splatters all over the ground, it's still not going to have any potential energy at position C. Well, if it's splattered all over the ground and it came to a stop, it's also not going to be moving, which means it doesn't have any kinetic energy. Well, this is a problem, because now it doesn't have any potential energy or kinetic energy, which means it's not going to have any total mechanical energy, which means energy is not being conserved. Well, why is this? The reason energy is not being conserved in this situation is because work is being done on the system from the floor. The floor is exerting a force on the egg that is taking away all of the egg's mechanical energy. So how do we represent that? Well, somewhere between the initial phase and the final phase, work was done on the egg that removed energy from the system. So the way we represent work being done on the egg is we draw the bar graph inside the circle, exiting the circle. So I drew an arrowhead that is showing that that amount of work is being done to remove energy from the egg. If energy was being added to the system, we would just draw an arrow pointing into the circle, showing that there's work being done adding energy to the system. So notice that my entire total mechanical energy is taken into consideration by the work that is being done on the egg, and it leaves the egg with no energy at the end. I hope this was helpful. Ta-ta.